Welcome back to Physics 141 Online. I've got one more example problem from Chapter 11 to work out. It's very similar to homework problems that you've done and even to previous examples that I've worked out. But in this case, practice may be what makes perfect. So the more kinds of problems like this that you can work out, the better you'll practice your skills. So let's read the problem. The helicopter has a propeller blade that can be modeled as a thin rectangular rod with length d and mass m. It's initially at rest, but it's free to rotate in a horizontal plane about a fixed vertical axis that passes through its center. So the idea here is this is the helicopter blade that's on top of the helicopter, not the small rotor that's near the tail. A projectile with mass m/4 moving horizontally with speed v0 along a direction perpendicular to the propeller hits the very end of the propeller and sticks to it. Find the angular speed of the propeller blade just after the collision in terms of the given quantities. And the given quantities, as you can see, are m, right, d, and then v0. So our answer should be in terms of those things as we need them. And of course we need a sketch. Really do need a good sketch. I'll just do it over here for simplicity. So the top view, what I'm going to draw is a top view showing that we have a propeller blade like this. Of course it rotates around an axis that goes through the center. Then there's a ball or blob of clay or some kind of projectile of mass m/4, and it's coming in. It's going to hit the very end of the propeller blade moving with a speed v0. So just to remind you, what we're looking at here is a top view. Alright, so that's just before the collision. Of course, the propeller blade has mass m and it's got a length d. So when they stick together, just after the collision, it's going to look something like this. Okay, the propeller blade, after the mass hits it and sticks to it, it begins to rotate. So here it's now moving around, rotating around that axis of rotation going through the center with an angular speed omega, and that's what we're trying to find. Okay, so we have fixed axis rotation. If we do an analysis similar to what I've done in previous videos and in class, we see that energy is not conserved. Kinetic energy is not conserved because the collision is inelastic. So we can't use energy conservation to figure this one out. We also know that momentum's not conserved because when the propeller blade and this mass begin to rotate, there's a force acting on them towards the center that keeps the whole system in circular motion, and that means there is an external force acting on the system, so momentum is not conserved. But that force acting on the propeller at the pivot produces a torque that's equal to 0 because the force is along a direction that passes through the pivot. So let me just summarize. Since the sum of all of the torques is equal to 0, we know that L initial, the angular momentum initial, is equal to L final. All right, I'll put vectors on those just to remind us that torque and angular momentum really are vectors. And that means what we have to do is find L initial and L final, set them equal. So L initial, the only thing moving initially is the mass m/4. It's moving at a speed v0, and it's going to hit the rod at a distance away from the rotation axis that's half its length. Right? So here we want to use the formula r perpendicular p, and we'll get the direction in just a minute. So here the perpendicular distance from the direction of the momentum that goes through the axis is d/2. Don't make the mistake of putting d in there. And p is simply m/4 v0. Okay, so we've got m v0d over 8. And let's get the direction associated with it. Once again, the direction is in the direction of r cross p. Remember that angular momentum in the vector form is r cross p. So for this object here, I'll draw a sketch over here. It's got a p vector, right, which is in the direction of the velocity vector to the right. The r vector is from the rotation axis to where the point is. Okay, so that would start at the rotation axis and go down and to the left. So I'll just draw that in like this. The r vector would look something like that. Drawing them tail to tail by the right-hand rule, curling your fingers of your right hand from R to P would give you a direction out of the page. Okay, so this is out of the page. We could call that the K direction if we want to, but I'll just leave it in terms of words. L final. All right, L final. The only thing that has angular momentum afterwards is the rotating object, which is now the rod or the propeller with this mass connected to it. So L final is equal to I total times omega. And that's the form that we use when we've got an object that's undergoing pure rotational motion. That's how we get the angular momentum. And we can look this up. We'll have to in a minute, because what we've got is I for the rod plus I for the projectile. Those two rotate together about the same axis. So we'll have to look up the I of the rod. It turns out that for a uniform rod rotating about an axis through its center, that first term is 1/12 the mass times the length squared. So it's 1/12 md squared. The projectile, if the projectile is small, we can treat it like a point mass, then it will have a contribution to the moment of inertia of the mass times the distance away from the axis squared. So it's m over 4 times d over 2 squared. And then that whole thing multiplies omega. Omega is what we're trying to find. So I can simplify this expression a little bit. Before we set it equal to the initial expression, we should definitely simplify it. I've got 1/12 md squared plus, let's see, 1/16 md squared. And if I want to get those over, both times omega, of course, if I want to get those over a common denominator, the least common multiple of those things is 48, and so this would be 4 over 48 plus 3 over 48. That's what those two fractions give me. I can factor out the md squared omega from both of those, and so you can see that gives me 7 over 48 md squared omega. So that's the final angular momentum. I'll set it equal to the initial angular momentum. What about the direction? Well, we can check the direction. It should be in the same direction as the initial one. If those two are equal, it's got to be. And if you curl the fingers of your right hand in the sense of the rotating object, in the rotational sense, which here is counterclockwise, if you curl the fingers of your right hand counterclockwise, your thumb will point out of the page. And so the directions are the same. That's great. We can then just set the magnitudes equal. So L initial equals L final. What that gives us, if we use that, L initial is mv0d over 8. L final is 7/48 md squared omega. We can divide both sides by the mass. It drops out. And one of the factors of d will drop out too. So let's, and then we multiply both sides by 8. So what I will have then is V0 will equal 8 times 7. The masses have canceled out. One of the factors of d has canceled out. D omega over 48. 8 over 48, right? That's 1/6. So this is 7d omega over 6. And what I really want to solve for is omega, right? So omega is equal to 6v0 over 7d. So I've got omega in terms of the given information, which included, as I said originally, the given information included m, d, and v0. The m dropped out, so apparently that term didn't really matter, and we have an expression in terms of v0 and d. And let's just check units. Units, well, the units of omega, we know what we expect them to be, right? And here we find that the units of v0 over the units of d would be the appropriate ones here. Well, v0 is meters per second, d is meters, and so we get an answer that will be in units of 1 over seconds. Omega we expect to be radians per second, which is consistent with 1 over seconds in this kind of an expression. And so the units turn out to be fine. That's about all we can do. So once again, this was a classic kind of angular momentum conservation problem where an object was translating, it hit and stuck to an object, after which they rotated together, and so initial angular momentum and final angular momentum are equal. And just remember that we use two different expressions. When you have an object that's translating, you can get its moment of its angular momentum about an axis by using this formula, r perpendicular p. On the other hand, when you have an object that's undergoing pure rotational motion, you use the formula I omega to get its angular momentum. All right, I hope this is helpful. Again, it's very similar to some of the problems you're doing for homework and that we've done in class. The more practice, the better. So I hope this helps, and I'll see you in class.